In the previous lectures, we had defined what is called the product measure on product space. In this lecture, we will specialize that construction on the set R 2. So, which is a Cartesian product of real line with itself, and the sigma algebra being that of either Borel sets or Lebesgue measurable sets, and the measure being the Lebesgue measure. So, the topic for today's discussion is going to be Lebesgue measure and integral on the space R 2. So, let us just recall. So, we had defined the product measure space. Given measure space is x, a and mu, and y, b and nu, we defined the product sigma algebra A times B on the product space x cross y and the product measure mu cross nu. So, today we will start looking at the particular case when x is equal to y equal to the real line, and the sigma algebra A is same as the sigma algebra B is same as the sigma algebra of Lebesgue measurable sets on the real line, and mu is same as nu, which is same as the Lebesgue measure. So, we are looking at a copy of the real line, the sigma algebra of Lebesgue measurable sets and lambda the Lebesgue measure, and taking its product with itself. So, that will give rise to the product measure space R 2, the Lebesgue measurable sets times the Lebesgue measurable sets, the sigma algebra, and the product measure lambda cross lambda. If you recall, we had mentioned that even if the original measure spaces are complete, the product measure space need not be complete. So, this product measure space R 2 lambda r cross lambda r and lambda cross lambda is not complete. So, we can always complete it, and that the completion is denoted by R 2, Lebesgue measurable subsets of R 2 and lambda of R 2. So, this is called the Lebesgue measure space. So, Lebesgue measure space is obtained from the sigma algebra Lebesgue measurable sets times Lebesgue measurable sets completed with respect to the product Lebesgue measure on R 2. So, this is normally called the product called the Lebesgue measure space on R 2, and the sets in the sigma algebra lambda of R 2 are called Lebesgue measurable sets in R 2, and the measure lambda of R 2 defined on this completed space is called the Lebesgue measure on R 2. So, whenever one refers to the Lebesgue measure space, it is the complete measure space obtained via completing the product measure on the product sigma algebra. So, today we will start looking at properties of Lebesgue measurable sets and Lebesgue measure. So, let us denote by I tilde as we have done for the real line, the collection of all left open right closed intervals in real line. So, let us look at the rectangles obtained by such intervals. So, that we denoted by I tilde 2 upper superscript 2 as I cross j, rectangles whose sides are left open right closed intervals. Then we claim that this I cross j is a semi algebra of subsets of R 2, and the sigma algebra generated by this is equal to the Borel sigma algebra of R 2. So, to prove this, we already know that I tilde, the left open right closed intervals form a semi algebra of subsets of real line, and we have already shown that if you take rectangles consisting of elements of the semi algebra, then itself form a semi algebra, namely the product of semi algebras is always a semi algebra. So, that general construction will tell that the space, the set of all rectangles with left open right closed intervals is a semi algebra. To show that this sigma algebra generated by the rectangles I tilde 2 is the Borel sigma algebra, we observe a few things. First of all, if you recall, we had shown so, let me just recall a fact that we have shown in the beginning of defining product sigma algebras, namely if we take a set x and take a set y, and here we have got a collection of subsets C, and we have got a collection of subsets. So, these are collections of subsets. Then we can form C cross D, that is a collection of subsets of x cross y, right. So, this is equal to all sets of the type E cross F, where E belongs to C and F belongs to D. And now, one can generate a sigma algebra out of this collection C cross D. On the other hand, we can generate a sigma algebra by the collection C. We can also generate a sigma algebra by the collection D of subsets of Y, and take the sigma algebra generated by the rectangles of this type. So, let us call it as S of C cross S of D. Then the claim is that these two are equal. Not always, whenever. So, we showed that these two are equal if x can be represented as a union of sets partition 1 to infinity, and D can be written as a union of some sets D j's in the collection D of 1 to infinity. So, whenever this x can be represented at a disjoint union of sets from C, and y can be represented as a disjoint union of elements of D, then whether you take the rectangles first and generate the sigma algebra, or generate the sigma algebras and then take rectangles and generate the sigma algebra, both will be equal to same. So, this result we had proved in the beginning of the topic. So, as a consequence of this, we obtained, so this implied one observation, that if you take the Borel sigma algebra cross the Borel sigma algebra of R, that is equal to Borel sigma algebra of the space R 2. So, that is one observation, because the real line can be represented as a countable union of, say, open sets or intervals. And similarly, the same argument also implies that if I take the sigma algebra generated by this left open right closed intervals cross the sigma algebra generated by left open right closed intervals, and then look at the product sigma algebra, then that will be same as the product sigma algebra of left open right closed intervals cross left open right closed intervals, because the whole real line can be written as a countable union of left open right closed intervals. So, these two facts follow from our earlier construction. So, we will keep that in mind. And now, what we want to show is that the Borel sigma algebra of R 2. Okay. So, that we know it is Borel sigma algebra of real line times the product Borel sigma algebra of real line, and Borel sigma algebra we know from our construction of real numbers, that is the same as the sigma algebra generated by left open right closed intervals. So, left open Borel sigma algebra is generated by the sigma algebra of left open right closed intervals. So, and this just now we observed is the sigma algebra generated by I cross I. So, that is same as the sigma algebra generated by I 2. So, that completes the proof of the fact that the sigma algebra generated by rectangles which are left open right closed intervals is same as the Borel sigma algebra of R 2. So, that is one observation. So, that is very much similar to the result in the real line, where the left open right closed intervals generated the sigma algebra of Borel subsets. The same result is true if we replace intervals by rectangles which are left open right closed. Okay. So, that is the proof we just now said. So, S I is equal to S I cross I. So, Borel sigma algebra B R cross B R is the sigma algebra generated by intervals left open right closed cross left open right closed intervals, which is same as the rectangles. So, now let us look at the next property, that the Lebesgue measure that we have defined for a rectangle is lambda of I cross lambda of j is same as lambda of I into lambda of j. So, that is obvious, because we obtained the product measure via extension of the measure on the rectangles. So, what we are saying is the Lebesgue measure on R 2 is the natural extension of the notion of area in the plane. So, this is property is obvious built in the definition of the product measure. And the third observation is, so recall we just now said that the Lebesgue measure space R 2, Lebesgue measures subsets of R 2 and Lebesgue measure, the Lebesgue measurable subsets. So, this space which is the space Lebesgue measure space, on one hand we define it as the completion of the Lebesgue measurable sets cross Lebesgue measurable sets, and this is also the completion of the measure space of real line with Borel subsets of R 2. And that is once again by the fact that the Borel subsets of R 2 are inside this, and the Borel subsets of R 2 and the Lebesgue measurable sets, they differ only by sets of measure 0. So, that is also the completion. So, one way of looking at it is look at the Lebesgue measurable subsets R 2, it being the completion. So, it is the class of all outer Lebesgue measurable subsets in R 2 with respect to the product measure. And on the semi algebra I 2 of rectangles, it is given by the product. So, this is obviously the completion of the measure space R 2. Okay. So, these are obvious facts. So, we should keep in mind which are very much similar to that of the real line. They plays a role later on when we want to look at null sets in R 2. So, basically the sets which are going to be of importance are going to be the Lebesgue measurable sets are Lebesgue measurable sets cross Lebesgue measurable sets in R 2 or Borel subsets in R 2. Here is another useful fact about Lebesgue measure in R 2, which connects it with the topologically nice sets, namely the Lebesgue measure of R 2 of any open non-empty open set is always bigger than 0. So, that follows from the fact that if U is contained in R 2 is open and U is not equal to empty set, then so here is the set U. So, there is always a rectangle left open right closed rectangle inside it. So, there is a rectangular neighborhood. So, implies there exists a rectangular, so non empty. So, there is a point x belonging to U. So, there is a rectangular neighborhood of x. So, let us call that neighborhood as n. So, this is the rectangle n which is contained in U. But the Lebesgue measure of, so that means the Lebesgue measure of U will be bigger than Lebesgue measure of n, which is always going to be bigger than 0, because it is a non-empty neighborhood. So, for every non-empty open set, the Lebesgue measure is always positive if the set is non-empty. And the second important thing is, supposing you take a set K, which is a compact subset of R 2. So, let us look at a compact subset of R 2. So, K is contained in R 2 and K compact. If a set is compact, that implies it must be bounded. So, K compact implies K bounded, and that means, so saying the set is bounded implies that, so this is the set K which is compact. So, that means it was bounded. So, it must be inside a rectangle. So, K bounded implies, so K bounded implies K is inside some I cross j, okay, with I lambda of I. So, implies lambda R 2 of K will be less than lambda of I cross lambda of j which is finite. So, finite intervals, compact implies bounded. So, there is a finite rectangle including it. So, that means it is finite. So, these are two relations about open sets and compact sets. There are more relations which relate like in the real line, that one can prove a result that, for example, a set E is Lebesgue measurable if and only if for every epsilon you can find a open set which includes it and the difference as measure small. So, that is very much similar to the real line, and the proof is also very much similar to the real line. So, we will not prove this result. An interested reader, if is somebody who is interested, should try to copy and the proof of the real line and extend that proof to the case of R 2. And similar, so that this will give us that another result is that for the Lebesgue measure of R 2, you can approximate it by this from inside by compact sets. So, supremum of lambda of R 2, where k is compact. So, these results basically are of importance. So, these are called regularity conditions for the Lebesgue measure in R 2. So, we will not prove these results, just for the sake of knowledge. I am mentioning these results here, so that later on if you come across, you can look at proofs of these results. So, the next result we want to look at is how are the Lebesgue measurable sets related with the group structure of the space R 2. So, let us take a subset E of R 2 and let us look at a point x vector x in R 2. So, we will define the translate of the set E by x to be as in real line y plus x, where y belongs to E. So, take the set E and shift every element of E by the vector x. So, it is y plus x. So, the first claim is that if E is a Borel set and the point x belongs to R 2, then E plus x also is a Borel set, that is one property, and the Lebesgue measure of R 2 of the set E is same as the Lebesgue measure of the set E plus x. That means, the Lebesgue measure is one says it is translation invariant on the class of all Borel subsets of R 2. So, the proof of this fact that for every set E, E plus x belongs to B R 2 and the fact that the Lebesgue measure of the translated set is equal to Lebesgue measure of the original set are standard applications of the techniques that we have been using, namely the sigma algebra monotone class theorems. So, let me illustrate this once again, so that this idea of using monotone class convergence theorem, monotone class sigma algebra technique settles down in the mind. So, we first want to prove, namely that we want to show that for every E a Borel subset of R 2, if I look at E plus x, that is also a Borel subset of R 2. So, the technique is as follows. Let us collect together all sets A. So, form the collection A of all those subsets E belonging to B R 2. All Borel subsets say that the required property is true, E plus x belongs to B R 2. So, look at all sets having this property. So, claim, so that is a sigma algebra technique. Claim 1, all open subsets of R 2 are inside this collection. So, we will prove two claims, one, and secondly that the class A is a sigma algebra. So, if we prove these two facts about the class A, then that will imply, because it includes open subsets of R 2. So, it will include the smallest sigma algebra generated by. So, these two facts will imply that the sigma the sigma algebra generated by open sets will be inside the class A, and that is equal to the Borel sigma algebra. So, that will prove that Borel sigma algebra is equal to A. So, let us first show that the open subsets of R 2 are inside A. So, let us take a open set. So, to prove the first fact, we have to show that if a set, so to show the first one, so let U be open in R 2. So, we want to show that this implies U plus x belongs to B R 2, and this follows because if U is open implies U plus x is open. So, that is a simple fact, because how do we show that U plus x is open? Basically saying that U is open. Okay. So, let us take a point y plus x belonging to U plus x. Okay. If y plus x belongs to U plus x, where y belongs to U, and U open implies there is a neighborhood. So, let us call it as B delta y. So, y belongs to a neighborhood which is contained in U, but then that implies that y plus x belongs to the translation of the neighborhood that is contained in U plus x. So, that means for every point y plus x, there is a neighborhood. When you shift a ball, that remains a ball in the plane. So, right. So, that is a basic fact we are using. If you translate a neighborhood, that remains a neighborhood in U plus x. So, that implies that if U is open in R 2, then U plus x is also an open set and hence belong to B R 2. So, that proves the first fact, namely open subsets belong to A. So, let us now to show that. So, this proves the first fact that open subsets belong to R 2. So, to show that A is a sigma algebra, that is this very standard technique. We have been using it very often. If a set E belongs to A, that means E plus x belongs to B R 2. So, let us write that. So, if E belongs to, so if a set E belongs to collection A, so that implies E plus x belongs to B R 2, and that implies, because B R 2 is a sigma algebra, so that will imply its complement belongs to B R 2. But this is same as the first taking complement and then taking translate. So, that belongs to B R 2. So, that means E complement belongs to B R 2. So, if whenever A belongs to collection A, its E complement plus x belongs to B R 2. So, that means E complement belongs to A. So, E is closed under complements, and similarly E i's belonging to A will imply that union of, so each E I plus x belongs to B R 2. So, that will imply that union of E I plus x belongs to B R 2 union over I, but this is same as union of E i's plus x belongs to B R 2. So, that will imply that the union of E i's belong to A. So, A i's belong to union also belongs to A. So, that will prove that A is a so A is an algebra. So, A is a sigma algebra. So, A is a sigma algebra including open sets. So, it includes everything. So, that will prove that. So, this is a sigma algebra technique I have been mentioning, that sigma algebra technique that we have mentioned says that implies that whenever E belongs to B R 2 implies E plus x belongs to B R 2. So, that is what we have proved.